In this video, we're going to talk about transformations of functions. We're going to start off talking about horizontal and vertical shifts that we call translations. And we're going to use the parent graphs or the library of functions that we talked about recently to be able to do that. I'm going to be using the Desmos graphing calculator to assist me in graphing these things on my computer. I recommend that you all graph them by hand using graph paper. But I'm going to have to use this so that you can see the ordered pairs here to assist you in graphing. So what I'm going to do is I'm going to identify first the parent graph of the function. Y equals x squared is the big thing that's going on in problem number 1 here. And the transformation is y equals x squared plus 4. And what I've done is I've gone into Desmos after I've typed in the function, and I've used the table feature to make it show these special characteristic points. And you can see that the red graph is my parent function here, and the blue graph is my transformation, and that every point has been shifted up 4, but it maintains the same shape. It's what we call a rigid transformation. Now, I'm going to keep the same parent graph of x squared in problem number 2, but my transformation now is going to be x plus 5 quantity squared, and my transformation is going to move every one of those points over to the left 5. So instead of shifting the y values, this shifted the x values, so you're not going to get a good image here of what happened unless I shift these for you and show you that that's -7, -6, -5, -4, and -3 there. And now you can see that these points have been shifted left 5, but they have the same y value. Let's put it together now, and let's do something with both a horizontal shift and a vertical shift. Let's make this x plus 4 quantity squared plus 5. And we can see now, hang on while I change these, that this is -6, -5, -4, -3, and -2, because I want my center to be at my vertex there at -4, 5. That'll be my vertex. Let me show you what I mean by that in vertex form of a parabola. We'll be talking more about this later when we talk about completing the square. That it's going to look like this with its vertex at HK, where H is the horizontal shift and K is the vertical shift. We can apply that idea more generally to some other types of graphs. Let me also identify that A here is the same A that's in y equals ax squared plus bx plus c. If I had written this equation that way, this A and that A are the same. And A is my dilation factor. And my dilation factor may also be responsible for reflection as well if it's a negative number. So this is going to stretch or shrink. Compress, let's say, the graph vertically. That will be our next video that we talk about dilations. We're only going to talk about translations today with this h and k. So more generically, we can get y equal to a times some function that I can put x minus h into and add a plus k outside. So we're going to see an example here in just a second where we're not dealing with a squaring function anymore. We're dealing with a cubing function. In fact, that's our next problem. I'm going to have to change the parent graph. Let me change my parent graph up here to be y equals x cubed. And now let's make this y equals x cubed minus 2. Let's change these all back to their characteristic points so that you can see that what I've done is taken every point and shifted it down 2. So red points have shifted down 2 to become blue points. Excuse me. There we go. Now I see the blue point at -1. There we are. And that is how you can graph them using your characteristic points from your parent graph and then shifting those points horizontally or vertically as the formula here tells you to do for the transformation. Let's look now at number 5. And it's x plus 3 quantity cubed. So you can already see what's happening here without me shifting the points here, but I would want to make this a -5, -4, -3, -2, and -1. And I would do that, then I would move all of my points to the left like so, and I would get new x coordinates, new xy ordered pairs where the x coordinate has been shifted left 3 and the y value stayed the same. I think you can see that now on the graph without me adjusting it in Desmos, since most of those are there for you. All right, let's try one with both a horizontal and a vertical shift. It's +1 inside and +3. And I'm going to go ahead and make this my set of points that have been shifted to the left 1, and then they are shifted up 3. So take this point and shift it left 1 and up 3, and we get that new centroid of the graph. The left 1 and up 3, and we get this new point that's 1 to the left and 1 down. Left 1 and up 3, we see as 1 right and 1 up, just like in the parent graph. If I was go 2 right from here, I would go up 8. If I would go 2 left from here, I would go down 8, just like on my parent graph. So I can use these values to tell me if I know where the centroid is, the center of the graph. I can use these instructions if there's been no dilation to tell me, well, that point stays fixed, that's in the center. And then the next point is 1 to the right and 1 up. And the next point is 2 to the right and 8 up. And another point is 1 to the left and 1 down. And another point is 2 to the left of the centroid and 8 down. That's how you can use your parent graph to help you graph some things like that. All right, let's deal with another type of function here. And we're not going to have all these points defined, as you can see. So I'm going to make a parent graph for this one that has X values that are perfect squares. Like so. And then since I am shifting vertically, I'll leave these X values alone here for you. These are the X values that correspond to your parent graph for that function. If you want 5 characteristic points, there they are. There's 16.4. I've shifted that down 5 and I get 16, -1. There was 9.3 because the square root of 9 is 3. I shift that down 5, I get 9, -2. I started at 4.2 because the square root of 4 is 2. Shift that down 5, I get 4, -3. 1 because the square root of 1 is 1. Shift that down 5, I get 1, -4. And I started with 0, 0 because the square root of 0 is 0. Shift that down 5 and I get 0, -5. I didn't actually calculate each of those things. I just took the 5 characteristic points that I knew and I applied the transformation to them and shifted them. And that kept me from having to stick these numbers in to the function and generate this t-table in order to make the second graph. Let's go ahead now, and instead of a vertical transformation, let's try a horizontal one. Let's stick x minus 1 inside. And since I'm shifting 1 to the right, I'm going to want to increase all these by 1. And let's see if I can zoom in a little bit on the graph. You might be able to see the transformation that has occurred. I might not get every single point here, but this red point right here at 1, 1 has shifted to the right 1 and has become 2, 1. This point at 4, 2 has shifted to the right 1 and become 5, 2. This point at 9, 3 has shifted to the right 1 and become 10, 3. And this one at 16, 4 has shifted to the right 1 and become 17, 4. So the whole blue graph is the red graph shifted 1 to the right. Let's try a combination now of horizontal and vertical shifts. Plus 7 on the inside and minus 7 on the outside. And I'm going 7 to the left. That's a -7. This is a -6. This is a -3. What I'm doing is I'm applying the subtraction of 7 to all of these x values here. It's 2, and that's 9. And we're going to go ahead and we're going to take a look at this graph now. I'm going to zoom out so you can see it. So we took this point that was at 0, 0, and we shifted it left 7 and down 7, and it's at -7, -7. We took this point that was at 1, 1, and we shifted it left 7 and down 7, and it's now at -6, -6. This point that was at 4, 2, and shifted it left 7 and down 7, and it's now at -3, -5. This point at 9, 3 shifted it left 7 and down 7, and it's now at 2, -4. This point that was at 16, 4, we shifted it left 7 and down 7, and it's now at 9, -3. Again, you may not get all of those on your graph paper. I'm able to zoom in and out here. I want you to see that we didn't have to calculate everything in this XY table. We can just move the points that we know from our parent graph, the characteristic points, to come up with those points on our transformation and keep the transformation with the same shape, since this is what we call a rigid transformation. It's like if you picked up something rigid, like a piece of metal, and you moved it left, right, up, down, it's not going to change its shape when you do that. It's not like a rubber band that's elastic that's going to stretch or compress. All right, let's deal with one more of these square root problems before we move on to a different type of function. This is now going to be x minus 1 on the inside and plus 3 on the outside. So this is going to be a 1, a 2, a 5, 10, 17. And when I've done that and shifted each of my x values 1 to the right, I've shifted all of my y values up by 3. I think you can see that in the table. And I think that you see that on the graph that I went right 1 and up 3 on each of these points. And they stayed with the same shape. The red function transformed to blue function. And I can see it shifted horizontally and vertically there. Again, if I get this new vertex over here at 1, 3, I can apply all of my characteristic points to say I'm going to go 1 right and 1 up, 4 right and 2 up, 9 right and 3 up, 16 right and 4 up, and I'm going to get my blue graph from that. Let's go ahead and let's talk about another one of the graphs that was in our parent graphs, our family, different family of graphs here in our library of functions, and that was the absolute value function. I'm going to use ABS for that, or I can use these absolute value bars in Desmos. It's shift and then the key that is above your enter key on a big keyboard. I'm not sure it would be where it would be on a phone or on a laptop keyboard. It should be in about the same place on a laptop, somewhere right below the backspace key. But let's go ahead and just use ABS for that, because that's how your calculator uses it. So most of your calculators will have an ABS function that's for absolute value. I'm going to do absolute value of x plus 3. And we're going to go back and put these characteristic points back to -2, -1, 0, 1, and 2 for that parent graph. And we have, this is a vertical shift, so I'm going to leave the characteristic x values alone in this case. And let's see now, left and right, I want to see that it's symmetric about the y-axis here. It has not moved left or right. And I get this nice V shape where every point on the right is reflected to the left, like so in the parent graph. And I get that again in my blue function, that these points on the right are reflected to the left. But we see that every point in red has been shifted up by a value of 3. So that's 0, 3. This is 1, 4. This is 2, 5. This is -1, 4. And this is -2, 5. Let's try a horizontal transformation now with an absolute value function. And since I've shifted the x values right 1 now, I'm going to do that with all of these. And you're going to see, zoom in a little bit more, that this point here has shifted to the right 1. This point here has shifted to the right 1. This point here has shifted to the right 1. This point here has shifted to the right 1. And this point here has shifted to the right 1. and that the whole red graph has shifted to the right one to become the blue graph. All right, one more of these types of problems, and then I'm going to work something out over here on the paper for you. It's fine. Let's go ahead and do a, oops, sorry, that's a -3 and a +7. And -3 is going to shift to the right 3. So we'll make this a 1, a 2, a 3, 4, a 5. And we'll see that we have moved from 0, 0 to 3, 7. And then I'm going to go right 1, up 1, left 1, up 1, just like my characteristic points tell me to do. I'm going to go right 2, up 2, and I'm going to go left 2, up 2, just like my characteristic points tell me to do. Right. That's everything for the drawing part. Now I'm going to make some calculations here. Give me just a second and I'll make my worksheet bigger for you so you can see my work. Okay, so we're on question number 14 here. And the question here is, if f of x has the point 2, 4 on it, then f of x plus 4, whatever that function was, I don't really care. What is the x plus 4 going to do when I add 4 to the x value inside the function? That's going to be a horizontal shift of 4 to the left. Four to the left. So that means that my new point, if I shift it 4 to the left, is going to be a -2 for x, and my y value stays the same. If I have f of x plus 10, this is a vertical shift of 10 up. So that means that the x value is going to stay the same. So the x value was 2. I'm going to add 10 to the y value. You may have seen those answers written there already because I did those problems earlier. So we're going to come back in the next video and we're going to talk about this idea of compressing or stretching. And I'll see you next time for that.